Okay, so maybe we can start this week's meeting. Yes. Now I realized that you have a new paper idea. So would you like to brief introduce that?
Yeah. So I just saw that music style transfer would be an interesting topic because there is not much success in that area, even though in image style transfer we have quite good results, and that's why I decided today to do my presentation about generative modeling, because I think generative modeling will be useful in order to work on this paper, and I will give a brief introduction about this type of modeling.
Okay, so you can first give the presentation about generative modeling, and then maybe you can say something about the paper idea.
Yeah. I just had an idea, but I have not went to very deep details. Yeah.
Okay. Okay, so.
But I can start. Yes, I can start.
Yeah, maybe you can start. Yeah. Thanks.
Generative models, as it might be clear from their name, are able to produce new contents. And to give you a more formal definition, generative models specify in terms of a probabilistic model how the data set was produced. Using sampling, we can create new data. And to give an example, suppose that you have dog images and you want to generate a dog image that looks like a real one, but it actually does not exist. This is a typical task for generative modeling, and here is a visual clue for you. We have training data, and we've fed this to our generative model. We have some random noise, and using sampling, we generate a new sample that looks like real, but that doesn't exist. I think it would be interesting to compare generative modeling with discriminative modeling, because this is the modeling about which you learned so far. And here you have label data, and you are trying to predict the label. So you want to classify it. This is a supervised learning. There is a comparison between what we are trying to estimate in discriminative modeling and in generative modeling. So discriminative modeling estimates P y given x, the probability of a label y given observation x. So we're classifying here. And in generative modeling, we estimate probability of x. So we are estimating the probability that we have an observation at all. And if the data set is labeled, we can also build a generative model that estimates the distribution Px given y. Now I will move to why should we use generative modeling. So it gives us complete understanding of how the data was generated and not merely categorizing objects. It seems highly promising in reinforcement learning, and it is my tier to acquire machine with the form of human intelligence. Of course, everything has some drawbacks, and generative modeling can be quite dangerous because it can produce fake content, and this fake content can spread throughout the internet. Now, generative modeling should be probabilistic rather than deterministic. So what does it mean? So if it was deterministic, then we will have fixed calculations, and we would get the same results every time. For instance, taking average value of each pixel. So this is not generative. It is essential to have some random element influencing each samples, as you saw from this picture. So we have here some random noise that influences each sample. And I just left here a quick note. This comparison for me was very similar to linear versus non-linear activation functions in deep learning. Now I will move to this node. Here I have a quick recap for some probability concepts, and I will read them for you. Sample space is set of all values that observation X can take. PDF a probability density function is the function mapping point from sample space to the number between 0 and 1. Area under PDF is equal to 1. Parametric models are density functions having finite number of parameters. Likelihood is defined as L theta given X and equals to probability of theta X. Maximum likelihood estimation is defined as theta equals to argmax L theta given X, and it is used to measure the set of parameters that are more apt to explain observed data X. So I just didn't put this here. I want to give you an example. Suppose that you have 10 dishes and your chef asked you to create a new dish. And you have also a recipe, and maybe you have some vegetables, fruits. Here, for instance, in the vegetables feature, you have potatoes, cucumber, and carrot. For fruits, you have tomato, strawberry, and banana. And also you have this salt and sugar, whether they contain it or not, and also if they contain this rice flour or just baking flour. I have here independent features which I will use in this example. In independent features, I gave this definition according to Naive-Bayes theorem. So if xi and xj are independent, then probability of xi given xj would be equal to xi. So, and also I have here a formula for maximum likelihood. So you would decide, for instance, to create such a dish which would be similar to those one, but is not the same. So this was your task, and you want to measure the probability of the values of the features which you are given, so that you will have the highest probability. For instance, you measure the probability of having carrot, strawberry, sugar, and rice flour in a new dish. And this would be equal to probability of carrot multiplied by probability of sugar, probability of rice flour, and strawberry. So that's how you do this stuff. But the main problem, I mean, this was very simple example where this might work, but we will not have always independent features. Suppose that we have images. If we will assume that each pixel is independent of each other, this would not work. So here comes representational learning, which is the backbone for generative deep learning models, and it tries to describe the samples from data X in low-dimensional latent space, and then it learns the mapping function, which will be able to take point in the latent space and map it to the original domain. So the strengths of representational learning are that it establishes the most relevant high-level features and gives novel representations with high chance that after mapping will look like real. For today, that was all that I wanted to talk about, and I think in the next meeting I will talk about variational autoencoders and generative adversarial networks, which will give you a better idea how generative modeling architectures look like.
Is there any questions or comments?
I think you're doing a great job. Just a quick question about the research question you added to the Word doc. Can you explain a little bit more about the research question? It was kind of difficult for me to understand the research question. I understand the context. I understand why you're interested in the topic, but exactly what research question are you trying to answer?
So I want, in this case, for instance, different style of to produce new style of music. I mean to, for instance, pop music and rock music, and then produce some new style of music. As I just thought so, that it would be interesting.
I mean, by research question, I mean, for example, in machine vision, we have a lot of interesting research questions. Like some old ones are, for example, I'm talking right now. How can you differentiate my voice, like my sound file, versus US sound file versus Jing sound file? How do you differentiate the three? Like classifying who is talking in this meeting, or identifying, like separating words from the sound file, identifying like the number of words, the specific words used, and so on. Or in like machine vision, we have a lot of research questions these days for automated vehicles, how to differentiate a passenger from an object that is like static on the road, and there are a lot of similar research questions.
Yes.
But all of these research questions are based on some problem behind the scene. Like there is a problem that we need to solve, and in order to solve that problem, we define this research question and we try to find an answer to that problem. So what specific problem do you have in mind? Like generating new styles for what reason?
I haven't thought about it in this way.
Like at the end of the day, you know why I'm asking this? Because whenever you want to start a new research project, you should think, like, not even just for research projects, for whatever you want to do, you should always think backward. Now that I want to start this new research project, I want to invest my time and resources to it. What will happen at the end of the day? If I'm very successful with this research project, if I can find a perfect algorithm that does exactly what I'm looking for, at the end of the day, who cares about it? When I'm authoring a paper about it and submitting to like popular conference, who is going to listen to my talk? Who is going to read or cite my paper? You see my point? If there is demand in the literature, like if you have read papers and some people are saying we need such a thing, or some people are talking about applications of this thing, or in like most of the papers have a future work section at the end of the paper or the discussion section. And in the future work, they're saying, so later on, people like other researchers, we encourage other researchers to do blah, blah, blah. If you find any mention of your ideas in those types of papers, like in future work or in open research questions, that would be very helpful because they would explain what is the problem behind the scene.
Yes, I actually read some general article, but it was also too general, and I found two research papers about this one, but I haven't read them. And I will read these papers, and I will give you a better information about it. Thank you for giving me advice. I will take it into account.
Great. So please, just to make sure we are on the same page, please keep in mind, just think about the idea of who is going to read and cite my paper at the end of the day if I'm very successful with this project. If you see anything in any part of the literature that is talking about the demand for what you have in mind, please summarize it on One Academy and present it in our next meetings.
Yes, I'll do that. Thank you.
Thank you.
Okay, thanks Neil for your presentation about generative modeling. So today we have Aryan, me, and Jean. We will give presentations. So Aryan, would you like to go first?
Yeah, I can go.
Sure.
Do you see the screen?
Yeah.
Okay, so I'm going to be talking about learning rate decay. And it's actually a really simple concept. Learning rate decay is the gradual reduction of the learning rate as a function of time. And this is done to speed up the learning algorithm. So as we run an algorithm and we approach the target or whatever, the learning rate eventually causes a lot of noise. So we find a way to reduce the learning rate over time so that we can converge on the target more accurately. And there's an example of why we need this. So I've used mini batch gradient descent to show. And suppose we take a constant learning rate alpha, and we can see here that's represented by the blue line. And as it approaches the target in the center, it diverges a lot and never really converges about the target. Because the learning rate is constant, there's a lot of noise in that area and it wanders around. It never really reaches the target. But if we decay the learning rate uh, as it approaches closer to the target, the larger steps it takes slowly get smaller and smaller. And this reduces noise and it allows the algorithm to approach the target. So it increases the accuracy. There are different ways to implement the learning rate decay. One of the most common ones is this one that I'm going to be talking about. Um, the formula is really simple. It's just alpha, which is the learning rate, equals 1 over 1 plus decay rate, which is just a tunable hyperparameter, so you can pick it, and the epoch number. So the epoch is the iteration we are making through the training set. So if you're making the second iteration, it would be 2. That times alpha naught, which is the initial learning rate. And I have taken an example here using decay rate 1 and alpha naught 0.2. And you can see that as we go through the first to the second epoch, uh, the learning rate alpha decreases. And the formula works because as we go through successive iterations, the learning rate decreases. And as I showed in the picture before, this allows us to converge more tightly around the target and decreases the step size basically. There's a few other methods for implementation. One of them is exponential decay, where rather than a fractional equation, we use an exponential equation, x raised to the epoch number. And x is an arbitrary constant that you can pick, which is usually less than 1. There's a lot of different formulas shown here, and I didn't really get a lot of information online about this, but these are the formulas that I could get. There is also manual decay in which you don't really use the formula because when you train one model at a time, you can manually decrease the alpha. So you can manually adjust the alpha to decay the learning rate. And periodically, you can just check it over the entire learning period and adjust how much you decrease. So, but it only works with like a small training set because you're doing it manually. Yeah, that's all.
Is there any questions or comments? Okay, so maybe I will start my presentation about RNN structure and forward and backward propagation. Can you see my screen?
Yes.
Okay. So actually, in the very first meeting, we have introduced a little bit about RNN basic structure. However, that time we haven't taken the recording, and also we have newcomers. Yeah, so today I will first give a quick recap of the RNN structure, and I have also added the back propagation part. So here you can see the simplest form of RNN is similar to a regular neural network, only it contains a loop that allows the model to carry forward results from previous neuron layers. You can see that compared with the regular neural network, there is an arrow pointing from itself to itself. So yeah, here is the unrolled RNN structure. You can see that the network looks at a series of inputs over time, like x1, x2, x3, and x4 in this picture. And for example, this could be a sequence of words in a sentence. Yeah, and the neural network has one layer of neurons for each input. At each stage in the sequence, each layer of neurons generates two things. An output YT, this is the model's prediction for what should be the next element in the sequence. It is here. And a hidden state, HT, this is the network's short-term memory. The hidden state is an activation function, which takes as its input both the hidden state of the previous step and the output of the current step. This allows the model to carry over information from previous step to the current step. You can, for example, you can see for H1, the input is H0 and X1, and and H1 will be calculated based on these two inputs. There is the formula for the math behind the simple RNNs. Yeah, for each neuron in the sequence, the output YT and the hidden state HT at each time, at time step t, can be calculated as follows. So in the first equation, you can see that the input is HT minus 1 and XT, and W and U are trainable parameter matrices, and B is the bias terms. This symbol denotes the sum up element-wise, and G1 is an activation function. So with the input HT minus 1 and XT, we can calculate HT. And then from HT to YT, we first multiply with another trainable parameter matrix, V, and then plus a bias term, and then apply the activation function G2, and then we will get the YT. That is the output at time step t. So when the network is trained, it not only assigns weights U to each neuron's input, but also discovers the weight parameter W of the hidden state function. These parameters define how much of the information from the previous steps should be carried forward to each subsequent step. So is there any questions so far? Okay, I will move on. Sorry. So here is the loss function for RNN. Give the predictions for each time step, that is YT, together with the ground truth labels. The prediction is Y hat T, and the ground truth labels are YT. We can calculate the loss on step T. We can apply a loss function, and we can calculate the loss JT. And to get the overall loss, we only need to average these losses on each step. You can see that J is equal to the sum of JT over time and divide by the capitalized T. Yeah, and if we want to minimize the loss function, we need to apply the backpropagation through time. So in an RNN, backpropagation needs to take into account that the model is carrying forward information from each neural layer to the next, and fine-tune the weights that govern this short-term memory. This is called backpropagation through time, and it uses the chain rule to go back from the latest time step to the previous step, and then to the next previous, each time using gradient descent to discover the best weights for each neuron and for the hidden state function. And then I will show you the formulas. Yeah. Oh. Okay. So for the RNN backpropagation formulas, let's start with a quick recap of the basic questions in RNN. So the first two are the forward propagation equation I have just introduced, and here is how the loss is calculated. So we want to calculate the gradient of the loss function with parameter u, v, and w. We can sum up the gradients at each step since the total loss is a sum of the loss at each step. So we can also sum up the gradients to get the gradients for the total loss. So thus we only need to find the gradient of the loss at each time step with the parameters u, v, and w. So for the derivative of v, it only depends on the current step. For example, you can see that here, J3, the derivative of J3 with V is, you can just apply the chain rule through the path J3, Y3, and yeah. So we can simply use this equation to calculate the derivative of V. However, it is not the case for derivatives of U and W. So we will take t equal to 3 as an example. To calculate the gradient of J3 with regard to W, you can see that when you go through the path from J3, Y3, and to H3, you can see that you cannot regard the H3 as a constant, since it also depends on the H2, H1, and H0. It depends on the previous layers of the hidden state. So to calculate the derivative of W, you have to consider all the passes and sum the gradient up. So the passes include from J3 to H3 and to H2 to H1 and to H0. And thus we have this equation. You can see that we sum from k equal to 1 to and to k equal to 3. And for k equal to 1, this represents the path from J3 to H1, and similarly for k equal to 2 and 3. Yes, and then we can have the equation here. Here we just replace the derivative of hk, of h3 with hk, and it is just another chain rule. For example, the derivative of h3 with h1 is just the h3 over h2 times h2 over h1. And this is also the same case as the derivative of u. For example, also we still take t equal to 3 as example. The passes we consider include from J3, Y3, H3 to H3, X3. And the second pass is J3, Y3, H3, H2, H2, X2. And J3, Y3, H3, H2, H1, X1. So we sum up the gradients, calculate with chain rule along all these passes, and we can get the gradient of the loss function with the matrices. So, is there any questions? Okay, so that's for my part today. So next I will we can move on to Jing, and she can introduce the vanishing gradient and also LSTM and GRU. Yeah. Jing, are you here?
Yes.
Yeah.
Just give me a sec. Okay, can you guys see my screen?
Yeah.
Okay. So, actually, I'm just going to introduce the GRU and LSTM this time, because those two are RNN extensions. So first, I'll introduce LSTM. So in the late 1990s, German researchers Hochreiter and Schmidt-Huber proposed the concept of long short-term memory, which would help RNN retains information over a longer period of time, not just in between two steps in time. For example, a character's name used at the beginning of a paragraph in a novel can be important for understanding who is speaking or what is being said at the end. LSTM RNN leveraging LSTM cell has the same architecture as a basic RNN, except that all its activation functions are replaced with LSTM cell. So what is LSTM cell? LSTM cell allows the network to pick up such pertinent information and save it, injecting it back into the model when necessary. While a basic RNN has only a simple activation function, an LSTM cell has 3 sigmoid activation function and 1 10H function. So the 3 sigmoid activation function output numbers between 0 and 1 and lead to a pointwise multiplication gate. This gate determines whether information should enter the cell or not. 0 means no information enters, and 1 means all the information enters. These 3 cells, these 3 functions or gates are used to save pertinent information for later stage of the learning process. And in the training process, the network learns what are the optimal values for the gates and how much of the information should be retained to help the network make the most accurate prediction. So here's a picture of the workflow of LSTM cell. So we can see there are 3 gates, which are corresponding to the 3 sigmoid activation function, and there's a 110H activation function here to in the second stage for the update gate, and we will introduce them one by one. So first, we can use the previous hidden state AT-1 and the current input XT, and with a set of parameter WF means forget, and BF, the bias term, and apply a sigmoid activation function to those terms and get a forget gate. And then we can compute the update gate in 2 steps. First, we use the similar function to compute the update gate, but with a different set of parameters, WU and BU. And then we need to calculate intermediate cell state candidate, which is C tilde T, use the 10H function. And then with all those 3 formulas, like the results from those 3 formulas, we can calculate the current cell state, CT, equals to the update gate times the intermediate cell state candidate plus the forget gate times the previous cell state. At last, we can calculate the output gate, also use the similar function but different parameters, and use the output gate and the current cell state to compute the current hidden state, which is AT equals output gate times 10HCT. And any questions so far? No. So I'll just introduce a little bit about the application of LSTM. So LSTM can be applied to a variety of deep learning tasks that mostly include prediction based on previous information. So 3 noteworthy examples include the first, text prediction. So the long-term memory capabilities of LSTM means it excels at predicting text sequence. In order to predict the next word in a sentence, the network has to retain all the words that preceded it. One of the most common applications of this is the chatbots used by e-commerce site. The second application is stock prediction. The simple machine learning models are able to predict stock values and the prices based on inputs such as the opening value and the volume of the stock. While these values do take part in stock prediction, they lack a key component. To properly predict a stock value with high accuracy, the model needs to take into account one of the biggest factors, the trend of the stock. To do so, the model needs to identify the trend based on the volumes recorded over the preceding days. So LSTM will be the perfect choice. And the third one is music composition. So LSTM can be applied considering that music is built using long sequence of notes, much like text prediction. Okay. So we know LSTM is a good way to retain information over a longer period of time, but the biggest advantage of this is computational cost is very high. You can see that we have four sets of parameters to calculate, and I didn't count the output layer like this. If you want to compute the output for each cell, you have another set of parameters to take into account. So that's why we introduced GRU. So gated recurrent units, GRU, resolve the vanishing gradient problems in simple RNNs, and also ease the burden of introducing a considerable number of additional parameters in the LSTM by dispensing with the use of a separate context vector and by reducing the number of gates to 2. So it only has a reset or relevance gate and an update gate. The purpose of the reset gate is to decide which aspects of the previous hidden state are relevant to the current context and what can be ignored. It computes an intermediate representation for the new hidden state at the current time. The purpose of the update gate is to determine which aspects of this new state will be used directly in the new hidden state, and which aspects of the previous state need to be preserved for future use. So here's the math behind the GRUs. So first, similar to LSMT, we need to use the previous hidden state and the current input and apply a sigmoid function to compute the reset or relevance gate. And then we can calculate the update gate similar to this function. And then we need to compute the intermediate hidden state candidate with the 10H activation function. But the difference here is we update the previous hidden state with the reset gate, the relevance gate. So we're not just using the previous hidden state directly, we update it. And then we can compute the current hidden state with the results from here. So HT equals 1 minus update gate times previous hidden state plus update gate times the intermediate hidden state candidate. And then we can compute the current output YT hat equals to an activation function. It can be anything like sigmoid or 10H or softmax. Yeah, and use the current hidden state times the weight and add the bias. Yeah, here's the workflow for this computation. Any questions? I think that's all for me today.
This was great. Appreciate it. So one theme I see in the presentations is focus on theory and applications. It will be great if we, in the future meetings going forward, it will be great if you can also add nodes like code snippets for how to implement this in Python or any language of your choice, so that we can just get more into some hands-on experience and we can start using some data sets to analyze, and whichever research project the team decides to go with, we can just start analyzing the data set corresponding to that research project, and we can just prepare ourselves for a research paper.
Yeah, sure.
Okay, thanks, Jing, for your presentation about LSTM and GRU. Yeah. Is there any other questions or comments? So I think that's all for our presentations today. And here is just a quick reminder that you can check out all the introductions of our research ideas in the detailed research plan under the file of our private channel. And you can also indicate your preferred research idea. There is a table at the bottom of the document. Okay.
Can I ask a question?
Yeah.
So there is a third research project on the list, and it's like, so it is like a application for students to like prepare for tests or something, and it uses like reinforcement learning, right? Or what?
I can explain a little bit more about that.
Yeah, just elaborate.
So let me actually, I have a couple of slides that I can quickly explain to you in the remaining time. Let me find the slides. Just give me a sec, please. Let me know when you see my screen.
Yeah.
You can see your screen.
Okay, so this is a project that I started in 2018. And it's about implementing cognitive psychology methods to improve students' long-term learning. So if you look at the literature, there are different practice tools. They call it spaced repetition tools. The most famous one is by Duolingo. So if you have ever used Duolingo, or if you have looked at their research, what you're doing is based on the same set of cognitive psychology theories. They call it desirable difficulties, like spacing, interleaving those things. So, by the way, this has nothing to do with deep learning, what I'm explaining. But later on, I'll tell you, in a few minutes, I'll tell you why we can use LSTM to like propose a better algorithm for this. So there are some popularly used practice tools. One of them is developed at U of M, at the University of Michigan. It's called Problem Roulette. I have not developed this one, but it is widely used in U of M and other schools. And the problem with this is that the students procrastinate. The students don't use it until deadlines, like exams. So you see no use, and before each exam you see a pick. So in the design of our practice tool on Runestone platform, we actually implemented a lot of different UX research ideas to motivate the students to practice throughout the semester. And the result was perfect. So you see, like, the students consistently use the practice tool. Like, there's the questions answered, total number of questions answered throughout the semester. And then in one study, in the study that I have cited here, we compared, in this study, I have explained the design of this tool and the effectiveness of the tool. So we compared the number of hours the students studied the textbook, because we monitor basically everything the students do in this class on Runestone platform. And we realized that after controlling for the number of hours of using our practice tool, the number of hours of studying has no statistically significant effect, almost zero. It's like this guy has a so significant effect that crowds out the effect of studying. So every hour of using the practice tool throughout the semester was significantly correlated with 1.04 percentage point increase in the final exam grade, which was a huge effect. In a more recent study, this is a working paper that I'm working on to submit to Science magazine. So we looked at 8 semesters. In a course, in each semester, we have about 200 students, usually more than 200 students. So in 8 semesters, we looked at the relationship between a student's GPA, prior GPA, and their final exam grade. So I'm using a standardized final exam grade here because the final exams are different. It should be comparable. So we see those students with lower GPA get lower grades in the course, which is kind of obvious. And those with higher GPA get higher grades. Although this sounds obvious, but this reminds us of a problem. And the problem is something that in economics, they call it poverty trap. If you have heard of Jeffrey Sachs's poverty trap book, or if you have ever heard of like poverty cycle or poverty trap, these are basically the same ideas. The basic idea is that those who are poor people, they're kind of doomed to remain poor. They're in the same cycle, the poverty trap. And those who are richer get richer over time. So because they have more opportunities, and they also have the incentive to compete with people in the same level to remain rich and get richer. And we see a similar phenomena in education, that those top students are always competing with top students, and they don't want to lose anything. They want to always remain top. Like someone with 4.0 GPA always wants to get 4.0 in every course. And the opposite is true about low GPA students. So what we were trying to do was, we were trying to apply these theories in the design of this practice tool to reduce this achievement gap, to provide an equal opportunity for low achievers and high achievers, so that anyone, regardless of their prior GPA, regardless of their belief about themselves, if they try hard enough, if they use the practice tool as we prescribed it, they can get high grades. And this is the result in the 4 semesters with the practice tool. So here we're comparing 4 semesters, the red one, without the practice tool, with 4 semesters with the practice tool. And we see we mitigated this issue. We mitigated this gap. Like among the low achievers, you also see that those who practice enough, they can get high grades. So you see a lot of complete grades, like 100% are among these people. So I don't want to go through how we designed it, but the result of the analysis shows that, first of all, using this practice tool significantly increases the final exam grade. That is one point of analysis. The other point is there is a significant correlation between prior GPA and exam grade, and by interacting this practice tool, we can reduce this adverse effect of prior GPA. Now the question is, how can we improve the design of this practice tool so that we get this benefit, and we can also make sure that the students answer questions? Like in this practice tool, how can we schedule answering questions in such a way that the students answer the questions that, let me actually show you another slide here. So what we do in this practice tool is that it monitors the time students spend on each problem, on each question, and we have many different types of questions. We have like multiple choice question, we have parse-on problems, we have active code windows that they enter like Python or Java programming code, and it immediately gives them response. It compiles their code or interprets their code and immediately gives them like personalized response about what's wrong with their code. Now, while doing that, we monitor the time each student spent on each problem, the number of attempts to get the correct answer, how close their answers were to the correct answer, and the number of textbook pages they looked at while answering each of these questions. Based on these, we have a very, very simple recommender system behind the scene that predicts when each student forgets each topic, right? And so here is the trade-off. This is the trade-off for which we need to use LSTM. So the questions are personalized based on this data, based on the history of previous answers for each student. If the question is asked from a topic too soon, a student wastes time. It means, like, if I have studied this specific concept right now, and an hour later, the practice tool asks me a question about this topic, obviously I know the answer. It's just a waste of my time to answer these questions, right? And it is boring because I already know it. It's not interesting to try to answer it. On the other hand, if we ask the question too late, the student loses the question, meaning that they try to answer the question because it is too late. They've already forgotten the concept. They cannot answer the question. And in cognitive psychology, specifically in self-determination theory, they call it perceived competence. What it means is that the student loses their perception of the competence to be able to study this course, to be able to answer these questions. They get a very bad feeling of, I'm not capable of continuing, right? So we need to do a trade-off between these two. And this is where we need a recurrent model like LSTM. Not necessarily LSTM, it can be any recurrent, any RNN, but basically I feel like LSTM is an appropriate model here, unless someone comes up with a better idea. And so what we need to do is we don't need to be very specific about time of forgetting, but we need to predict their forgetting curve to figure out which day they're going to forget this concept. And after identifying that day, the system will ask a question, a random question from that topic a day before the predicted forgetting date, right? So I've shared a paper in the, I think I've also shared this paper. This doesn't have anything to do with deep learning. There's just a very simple algorithm. The main point in this paper was the UX design of the system. I've also shared a link to another paper. Let me open Microsoft Teams, deep learning. So you can find the research questions here. Yeah, here is the research question I added. So this is the link to that paper that I just showed you. I was talking about this actually. This paper is a good one. It is using reinforcement learning and like using deep learning and reinforcement learning, and they're trying to do basically a similar trade-off to identify when each student is going to forget each specific topic. However, one of the problems in most of these studies is that they work on language learning. Most of the papers published by Professor Lewis or in general the Duolingo team is about language learning. And there is something very specific about language learning. In language learning, you don't have relationship between concepts. Words are distinct from each other. If you learn one word or the other one, it doesn't matter that much. The important point is, like, words are not interconnected. However, when you're talking about a college level course, or like a topic like programming or medical science or something like that, similar to the type of stuff that you see on One Academy, concepts are related to each other as you are drawing these prerequisite links, right? So specifically in learning programming languages, concepts are very, very interconnected to each other. If you don't understand for loop, for example, it is very difficult for you to understand recursion, something like that, right? So the LSTM model that we developed should embed two things in the network. First, the history of students' answers and their behavior over time, each student's behavior over time on answering these questions. Second, the network of relationship between questions should be also embedded in the network. Now, there are two approaches. We can actually design new variables as inputs to the network to feed into the network, like the kind of like previous history of answers by each student, or in terms of the second case, the relationship between concepts, saying that like this has this many prerequisites, or this is related to like these topics, and so on. There are a lot of types of encoding that we can use to embed this data and feed it into the network, or we can feed the raw data and we can design the model by tuning the hyperparameters in such a way that finding relationship between, like the network of relationship between concepts and the history of answers to these questions gets embedded in the network of LSTM or whatever recurrent model we're using. Does this make sense to you? Do you have any questions?
Yeah, it seems right. So we're using like LSTM to predict the day when the person will probably forget something and trying to, yeah.
Exactly. And
see.
something, a good opportunity we have in this project is that we have a huge data set of students' answers to questions over a semester in both Python and Java languages. So this system that I've built, it is not being only used at U of M, it is also being used at Coursera. So we have, I think, around, so far we have had more than like 7 million students using my practice tool on Coursera for learning Python 3. And also, last week, I realized that for Java programming, there are also a lot of more than 1,700 instructors in the US who have been using my tool in their classes in high schools and universities for teaching Java. So we have a lot of data, but we should start with a small data set. We should try to just understand the data set, understand the problem. We should try to, first of all, I feel like before looking at the data, we should definitely go through the prior literature, like Duolingo papers or the paper I shared with you, or other similar papers. There is a lot of ongoing research on the topic. This is a topic that, like every year in like ICML or KDD, these conferences, you see at least 1 or 2 papers on this topic. It is a very active topic. So we need to look at the literature. We need to understand what others have done and what others are doing. I feel like we have a unique opportunity that while everybody else, almost everybody else, as far as I know, is working on language learning data, we have a lot of data for real college level course learning. And I feel like this can be a unique opportunity that others have not had in the past. And our algorithm, if we can do a good job, our paper may get a lot of citations. And there may be a lot of other people who follow the algorithm that we propose, and they use our data sets, they continue with making the algorithm more advanced. But that is the basic idea.
I see. Okay, thank you for explanation. I get it
Sure.
now.
Any other questions?
No?
Thank you.
Yeah, thanks, Iman, for the very clear explanation of the paper idea. So if there is no other questions, we can end today's meeting. Okay, so see you. Have a good day.
Bye.